So we can thank COVID for this infrastructure where we can record some lessons here and there. Okay? So I guess there is a positive. I'm not sure. Is it really a positive? I am going to remind you, though, that when you're watching the videos, however you choose to watch them, you can play me back at like double speed. You will not hurt my feelings. You can pause me and leave me for hours on end, and that's okay as well. Hey, yeah, Mr. Harper. Jeez, it's interesting because wow, I love 16. I think it's one of the best questions I've asked. I don't think I'm gonna answer 16 today. Let's see how the day goes. Okay, and maybe because like it's okay. I know it sounds a bit weird to say this, like the struggle in math when you're trying to figure out something only adds value to the experience when you finally figure it out. So if I take away the struggle, I'm actually making things less fun for you. I know that doesn't sound right, but it's true. All right, I did want to take a look at number 4. There's a segue here that's important too, because I do want to get into 1.4, the concept of inverse, if we can get there today. And if we don't, I guess that's okay. So this is from the handout that I gave you yesterday. It's just mine's in color. So this is the bottom. This is the handout 1.3. Does it? Oh, yeah. So you know what we're going to do? We're going to do my favorite thing. Okay, you ready? Because this is the only reason I wanted to become a lawyer is so I could redact. So we're just going to redact this. Yeah, I changed the best question, so don't panic. Don't worry about it. There's nothing for you to see here. Okay. Just that I had an older version that I printed into OneNote. So the handout that I gave you, the physical handout I gave you is the correct one. So maybe you could help me out. The best questions are supposed to be, aren't they supposed to be like 11, 15, and 16? These are supposed to be the best questions. So maybe what I can do is undo the entire redact and just redact this and this. Are we okay? Does that make sense? It's just because I updated it and changed it, but I didn't change it in OneNote initially. Okay. All right. Thank you for noticing that. All right, first question. So I like this question. This is very consistent, sort of like with the provincial standard. First thing I want you to notice as we go through this is, can you see the origin is given to you? So as soon as you know the origin is given to you, you already know what your shifts are, not your stretches. You just know your shifts. And it's good practice, I think, over the years is just to write them out so there's no misunderstanding later on. So it seems to me that we've got a horizontal shift. And if I look at the instructions here, it looks like we're moving 7 units. And I'm just going to say to the left, okay? And I'm just putting the wording in because I think it's easier to translate. And later on, do you see there's a vertical shift? And in this case here, it's pretty clear that it's 2 units up. Now let's talk about the stretches. And I use the word spans when I talk about stretches. The first thing I want you to notice is that the horizontal span, the distance from left to right, is 4 in the original function. And now all of a sudden the horizontal span is, well, it's only 2. So my question to you is, what do you do to 8? Are we clear that this is indeed 8? I'll use a different color. What do you do to 8? What do you multiply 8 by to generate 2? We got 3 different answers there. What do you multiply 8 by to get 2? 1/4. Okay, so then all I want you to do here is, right, you've got a horizontal stretch, right, by a factor of 1/4, okay? By a factor of 1/4. Okay. And then lastly, is there a change to the range, to the y values? I think the answer is yes, there is. It looks like initially we've got a range here, or a span, a vertical span of 4. And if you look at the red function, if you add it up, it's got a vertical span of 8. How does 4 turn into 8? Perfect. So we have a vertical stretch by a factor of 2. All right, now can we take all of this wonderful language that we've written and turn it into the transformational language that we're looking for, right? So you're going to tell me that our It's in red, so I'll write it in red. Our function g of x was created by the following transformations. There was a vertical stretch by a factor of 2, f of hard bracket. It looks like we got a horizontal stretch by a factor of 1/4. That means your b value is 4, right? Because you're traveling 4 times as fast, so you get to your destination in 1/4 of the time. Soft bracket, we got a horizontal shift 7 units to the left, so you better write this as x plus 7 to get that shift 7 units to the left. And then last but not least, we're just going to bump this up 2 units for our vertical shift 2 units up. Final answer. We like that? A little bit? Okay. But can you see that if I write it out, I know I'm going to get it correct. Like if I write it out, the words in blue, I will get it correct in the transformations I've written in red. Because I know when I asked you that first question, some of you said 4, some of you said 1/4, somebody said 1/2. We got mixed values for our possibles for B, correct? All right. Next, I'm actually going to segue. So if you've got this booklet out in front of you, I want to show you this because this comes up quite often and teachers like this sort of test for transformations. It's called the Keypoint Example. And I think we came up with it because it's a really, really easy way for us to test, do you understand the nature of transformations? And instead of talking to you about it like a function to a new function, how about one point transformed into another point? Because you got to think, isn't that what happens with a transformation? Isn't it just a transformation of a bunch of points? All right, so I'm going to give you a function. I'm a very generous guy, so I'm going to give you a function. I'm just going to tell you it's f of x, and that's all the instructions I'm going to give you. I don't know what this function does. I don't know if it's absolute value, if it's square root, if it's squaring, if it's logarithmic. I know nothing about this function. I'm just telling you it exists. And even better, I'm going to tell you this function passes through a point, and I'm going to give it a name. I'm going to call it A just for reference, but more importantly, I'm going to give you the coordinates of it. The coordinates are 2, 3. So we've got a function. I don't know what it's doing, but I'm telling you, it passes through 2, 3. And then it makes sense if I decide to transform this function, should it not also transform our key point? Hence the name key point. Okay. Well, I'm going to tell you this new function, g of x, I guess we decided g of x is always going to be red, is created by the transformation of f of x. And there's all kinds of shenanigans going on. First thing we're going to do is we're going to do like a vertical stretch by a factor of 4. So 4 f hard bracket. And then inside, I'm just going to write it out first. I'll worry about what it does later. But inside, it's going to be like -2. Actually, I'm going to write it as -2x minus 10. And then at the end, just for fun, we'll add 3. Your job then, if it's okay with this notation, can you find A prime? In other words, the new location of A after we've transformed it. And it looks like we've got 1, 2, 3, 4, 5 transformations that are occurring here. Can you see there's 5? Vertical stretch by factor of 2. A reflection horizontally, so a reflection over the y-axis. We also have a horizontal stretch, a horizontal shift, and last but not least, a vertical shift. All right, well, Joel's here. What's Joel going to tell you to do first before you do anything? Factor, right? Okay. So, and he's right. Like, if you don't factor this, this is not going to go well for us, is it? So the first thing you're going to do is you're going to rewrite this as, this is going to be g of x equals, the 4 doesn't change. The function we know nothing about doesn't change. But when you factor this out, be careful. Factor out -2, leaving behind x plus 5 plus 3. So all we've done is we factored out the -2. And then if you're not sure if you factored out correctly, you just multiply the -2 back through the brackets. Like, does -2 times x create -2x? Yes. But more importantly, does minus 2 times plus 5, does that create minus 10? It does. All right. Then what I would do if I was in your position is I'm going to remind myself that when we consider x comma y, which is the description of any point from the original function, and then we apply the transformations, can we describe what those transformations are? All right, Mr. Harper. What are the transformations that are going to happen to our x coordinate? Absolutely spot on, lovely. That's correct. Those are the transformations to x, right? You're going to reflect it. You're going to stretch it by a factor of 1/2, and then you're going to subtract 5. Lovely. And then on the outside looking in, what are we going to do to our y coordinate? Lovely. And then now that we know this, can we take the point that we were given? Remember, we were given a specific point. We were given the key point, and the key point just happens to be 2, 3. Can we allow our point to enjoy all of these transformations? So if we go through the process, you're going to do minus 1/2 of 2, subtract 5. That's the changes, all the changes to x. Then you're going to do 4 times 3 plus 3, so we can see all the changes to y. Clean it up. And when you clean it up, it should turn into, what do you want me to show you? It's going to be, I love the first fraction, gives me minus 1 minus 5. The other, I guess, is 12 plus 3. And then final answer is minus 6, 15. Are we okay with that? Can you see why a math teacher would like this question? Mainly because you don't have to draw anything to confirm that what the transformations are doing. And I'm pretty much warning you or telling you that there's a version of this type of question that will show up not on Tuesday, but will show up on your assessments, your major assessment when we do the unit test in the future. Okay. All right. This segues back into, you ready? Number 3. How many of you enjoyed number 3? And it's interesting because in this question, like I looked at it a few times and like I think it's a good question. I also think it's a tough question. But first things first, like any good math person, make sure you get the marks you know how to get. Is it true that they gave you the origin? So we don't have to think about our stretches at all. Sorry, I said it wrong. We don't have to think about our shifts at all. So right away, you could tell me, based on this information, don't we have a horizontal shift? And if I say this correctly, it looks like we're going 3 units to the right. And we can only do this without any fear because, well, we're working with the origin, and the origin can't get stretched. And then based on this information as well, there's also a vertical shift. And if we look at our instructions, it looks like we're doing, is that me? Oh, it's you. Okay. Sorry. 4 units down. So we got those 2 pieces done. So here's our problem though. How on earth are we going to figure out the stretches? And I got some bad news for you. Oh, did you figure a way out, Magnus? So your suggestion is, look, I get it. So if you I kind of like it. He's saying, look, let's undo the shifts, right? But you're still going to honor the fact that this function is here, and it looks like you go 2 steps left, 3 steps down. So 2 steps left, 3 steps down. And could you just draw the stretched version of this function? Is that what you mean? Okay, I like that. And then it's not the way I did it, by the way, but it doesn't mean like I own the only way. There's lots of ways to solve problems. I like that. So you're just ignoring the shift. You're kind of ignoring the problem. I like denial. Okay. So where are we going to go next in this conversation? Because I still need to find the stretches, right? So what did you do, Matt? Did you count the spans? Is that the word I'm using? The span. So which spans did you count? Oh. So did you like, are you comparing like this span here? Oh. Okay, so appreciate this. I like this. So you compared this span. Oh, that's pretty cool. So you compared this span here. And then did you go down 4? Why did you? Oh. Oh, I see. And this is okay. And then you figured out, because I'm trying to figure out your thought process. And then you said to yourself, you went 4 units this way to achieve the same 3 units that way. Hmm. And did you describe only a vertical stretch? Did you check to see if your solution matched in Desmos? It's a good question. We could have a big tangent today. Ah, I I I I like your thought process, but I'm not actually convinced that your final answer is true. All right, here we go. I'm I want your answer to be right, so I'm not officially telling you that you're wrong. How about that? Okay. So I agree with Jovi. So I'm gonna sorry, Magnus. So there's a reason why they gave you these points, right? So this is the points 1, 1, and I think the corresponding point is over here. Isn't this the point, if you look at it, is this not 5 and minus 7? Okay. And is it, yeah. Okay. Okay, but even if it was reflected horizontally, it wouldn't change the end result. Okay, so we got to be careful here because this could go sideways and we could spend a lot of time. So what you're saying is true. Okay, I'm not going down that rabbit hole. You're talking about, we call it an even function versus an odd function. An even function is symmetrical about the vertical axis. So you don't know that you've reflected, because if you reflected it, it still looks the same. So that's frustrating. So what you're saying is true. And that's called an even function. And we kind of ignore it because it doesn't matter if you applied or don't apply. Okay. So and I don't want to go down that tangent because then I have to tell you what an odd function is, and we don't have time for that. But that's a great question. I may get to it later on when we talk about something else. Okay. Okay. All right. Here we go. This is what I needed you. Well, I need you guys to do lots of things, but this is what I wanted you to notice. Okay. You ready? I wanted you to notice that we started off with the orange point. The orange point was 1, 1. Stuff happened. And is it safe to say, I guess I got to go green. Is it safe to say that we ended up with a new point 5, comma, minus 7? Is this true? Let's start the conversation there. We had 1, 1, and I'm arguing that 1, 1, I know we reflected it, I know that we shifted it, and I know that we stretched it, and we end up. So these 2 points are corresponding. Can you see this is like the key points? This is like the key point example, and then this is the new point, and it's like we're trying to figure out the transformations in reverse. Okay, I'm ready, Mr. Harper asking.
You've checked that most so that it doesn't work.
Okay, so then we're gonna have to have a debate later because my solution, I feel, is a little different. It doesn't necessarily mean that he's officially wrong. Okay, that's what I got. Same. Oh, we have dissension. We have dissension. Okay, but that's okay. I like the argument. This is good. Or the heavy negotiation, that's what we'll call it. And I'm going to show you the technique that I used. And Magnus, I hopefully you could appreciate it just as much as I appreciated yours. I still haven't officially said that you're incorrect. Okay, all right. And is it safe to say that, like, if we were talking about this particular function as we try to organize the pieces here, right? Could we sort of partially describe what the changes are? Like, is it safe to say that when we're creating g of x, I don't know why g of x is red, but when we were creating g of x, what do we already know to be true about the transformation of g of x? So I don't know yet what the vertical stretch is, so I'm just going to call that A, right? F of hard bracket. I still am not sure what the horizontal stretch is, so I'll call that B. But don't I already know what the horizontal shift is? It's like 3 units to the right. So if it's okay with you, can I write this as x minus 3? Like, I know that to be true. And then at the end of the day, aren't we shifting this thing 4 units down? Okay. Now, I'm trying to create something that allows me to solve the problem, and I think I can, because it says to me, whatever point I start with from the original function, right, if I want to find out what the corresponding point to the transform point is, wouldn't I think of it this way? Wouldn't it be 1 over bx plus 3? Aren't those the transformations that should create the new points, the green points, right? And then based on this information, if I do AY subtract 4, isn't that the transformations that should create the new green point, the Y value of the green point? Well, we know who the original point was. The original point was 1, 1, right? That was the original point. And then weirdly enough, we actually already know our destination. Isn't our destination 5, comma, minus 7, right? That's the end result. You ready? I can build 2 separate equations that are help me find the 2 missing pieces. Our 2 missing pieces are the B value here and the A value here. You ready? Isn't it true that if I take just the X values here, I know if I take 1 over B and then multiply it by the original X value 1, and then add 3 to it, isn't my destination 5, comma. I know if I take the original Y value of 1, and I'm supposed to take A times the original Y value of 1 and then subtract 4, isn't my destination supposed to be minus 7? Have I built 2 very convenient 2-step equations? Learn them in grade 9, lots of fun. But we call them linear equations to allow us to solve for both of these. So if I continue forward, doesn't this just give me like 1 over b is equal to 5 minus 3, which is 2? And if I cross multiply and solve, is it true that b itself has to be 1/2? Are we good with that? And you can check the math. I'm assuming at this stage here, we're relatively comfortable with a linear equation. And then over here, this is just going to be A is equal to minus 7 plus 4, which just happens to be minus 3. Okay. Now we can celebrate mathematician style. You're going to tell me, therefore, our transformation of g of x, can be described as the following, right? Your A value was minus 3. F of soft or hard bracket. Our B value is 1/2, but we're not going to write 1/2, are we? Oh, no, we're going to write 1/2 because that's the B value. Excuse me. The B value is exactly 1/2. And then it's going to be x minus 3 and then minus 4. And I checked it because I was interested in it. Is it exactly true? And the answer is yes. Do you want to see the check? I'll show it to you quickly because you're asking me a good question. Okay. So I just jumped into Desmos. Again, it's the happiest place on earth. And again, you are welcome to use Desmos as much as you like. And it saddens me a little bit that you can't actually just use it on the test. We know from the diagram, it doesn't take us very much to realize that the initial function here is indeed x squared. You can check it if you don't believe me, but that's the function. It's x squared, right? Yeah. like that. And then I just change the color because this is like the parent function. In my mind, the parent function is always black. I don't know why. All right. Then in the instructions, I'm telling you, our g of x is in fact a transformation of this function. And we described it as follows, right? It was -3 f. Now, it doesn't really have like the hard cold bracket that I like to use. So I'm just going to use an open bracket. And then it's 1 divided by 2 because that's 1/2. Another open bracket. And then it has to be x minus 3 because that's going to give us the horizontal shift. And it's kind of cool, right? Because you could see as Desmos is applying the transformations as we move forward. Hold on. And then last but not least, according to my description, don't we bump it down 4? And is that exactly the same as the image that you have in front of you? And the answer is yes. So your Desmos understands transformations of functions, doesn't it? Okay. Are we okay with that? You like that, Katie? I'll come help you with it later. Okay. Yeah.
How does it, like, how does it know that it's a parabola of a square?
Oh, well, because when I use this symbol here, F, and you notice how it reoccurs in here,
It knows that.
yeah, so it's just like a computer program. So what it's doing is g of x is being defined by all of the changes to something called f. You declared what f was here. So it just reads back up a line and it just inputs all this information.
And that's also why, like, whenever you write in a question, or like you already have f of x, so that's how we don't rewrite.
That's right. Now you're gonna like this because we're having some fun with this. What happens if I change f of x? So let's say we make it the square root of x. You guys are right. But all it's doing is it's applying the same transformations, different function. And I know I scared some people with this concept a little bit a couple days ago. We do more than just play around with the square root of x and x. What about a trigonometric function? I don't know, but Desmos can help me, right? Desmos can graph way faster and better than me, right? So you're asking me what would the reciprocal be? So 1 divided by the square root of x? I don't know. I'm a little bit afraid. Oh, okay. I'd have to think about more why that's the case, but it will do it for you, right? And again, I want you guys to enjoy Desmos. It's just changed how we teach high school mathematics in the last 15 years. Good? All right. I'm avoiding number 16. I will come back to number 16 from the homework. I think it's a great question, so we'll do that. We're going to jump into 1.4. If we can find it, so 1.4. I don't know that. So 1.4 is inverse of a function. And again, the nice thing too is that this is recorded, so I'll organize it. So you can always go back in and watch it again if there's something that you want to see. If you want to replay it, so you can do it as many times as you want. And if I put it on YouTube, maybe at some point, if you guys watch it enough, it will be monetized, and I can submit. We'll just move on.
Well, you have to have a thousand likes.
Yeah, I have maybe 2 subscribers, okay, and I might be both of them. All right, here we go. So inverse of a function. So inverse is an interesting concept. Because when I say inverse of a function, what I'm really describing is, and I like this expression, I don't know if it's all mine, but it's somewhat mine. The inverse of a function is simply the undoing, okay, the undoing of the doing. The undoing of the doing. Sounds really awkward, but something happens and then you want to undo it. And I don't know why I thought about this story this morning, but Many years ago, my brother was chasing me. My older brother was chasing me, and we're coming through the back door, and I didn't want him to get me. I'm sure I stole something of his or his toys or something, or broke something. He was mad about something. It doesn't matter. And as I come through into the kitchen, I slammed the back door because I didn't want him to get to me because he's bigger and larger. And then as he's coming in, he puts his hand forward and he puts his hand right through the window of the back door. There's glass everywhere. And in that moment, he didn't understand what inverse means. Because he made the mistake because he put his hand through the window, he just pulled his hand straight out, right? And when you do that, what tends to happen is you're going to lacerate, you're going to cut up your hand on the way out. If he understood the concept of inverse, the concept of inverse would be he would stop, take a deep breath, and then slowly pull out his hand in the exact opposite direction, and then he wouldn't have actually hurt himself. Yeah, okay, a little bit, but not as much as he actually did. I guess what I'm trying to say is in mathematics, it's important for us to understand sometimes we want something to happen in a particular order, but sometimes we have to undo what has happened in the exact opposite order. And if we don't do it in the exact opposite order, sometimes bad things happen. All right, so here's our first sort of scenario, and we're going to keep it really straightforward initially. So I introduced to you a function. You know me, that's all I do. I just throw functions at you. And this is a very friendly function. It's 2x minus 3. So it's a linear function. It's a well-behaved function. It's a continuous function. We like this function. Okay. And when I take a look at this function, I guess what I want to do initially is, can I undo what's being done? Well, question, what's being done? Can we use this notation real quick? If I said to you, hey, let's do f of, I'm going to pick a nice number. Let's pick 5, f of 5. What I'm asking you to do is, I know this is slightly new notation for some of us. I'm saying, I want you to take 5, that's your input, and I want you to put it inside the function and see what the function's actually doing, right? And based on my information, it's going, oh, it's going to take our value of 5, and the first thing it's going to do to the 5 is, well, it's going to multiply it by 2, right? Because isn't that what our function does? And at the end of the day, it's going to subtract 3. So 2 multiplied by 5, subtract 3. And if I do the calculation here, I guess is what, 10 subtract 3. The end result of this is 7, correct? Can I introduce to you another function? And this function claims to undo everything the first function did. And sadly, I'm sorry, I can't help it. It's called g of x. Okay. G of x shows up, and g of x is going to try to undo everything that the first function did. And the description of this particular function is going to be x plus 3, all of which is divided by 2. Okay. How would we figure out if this function actually undoes all the hard work of the first function?
Put the same value.
Put the same value in?
Put the inverse value.
Careful. So we know where we ended up at the end of the day. The question mark is, will our function take us back home? So I like this, what you said. We're going to try g of 7. And if g of 7 does what it's supposed to do, we should return back home, shouldn't we? So if we do this here, I'm telling you, you're putting 7 into the function. And based on our information, we're going to add 3. And then the last thing we're going to do is divide 2. And if I follow through with this, isn't this 10 on top divided by 2? Do we return to 5? Now can we talk about some of the things that we notice here? In the first function, what was the first thing we did to our input, to the 5? Multiplied by 2. What's the last thing that we did in g of x? We divided by 2. What was the last thing we did in the first function? Right. What's the first thing we did in the inverse function? Do we notice the pattern? I said to you, I'm thinking my brother tried to take his hand through the window. He needed to pull it out in the exact opposite order to avoid injury. Okay. All right. Well, there is an algebraic technique that allows us to find the inverse. Okay, of course, right? That's why I'm here. So if we travel back here and just ignore this question, I just said to you, hey, I got this function, f of x, and I'm going to describe it as, I'm going to change it up a little bit. Let's make it like 3x minus 5. Still linear, still relatively straightforward, a friendly function for now, okay? And what I want you to do is I want you to find the inverse. But I'm not going to make it as challenging. I'm going to give us a nice algebraic technique that's going to help us find the inverse. And lots of people like this. In this case here, when we describe it to you, I'm going to say, well, first things first, it's just convenience. Just because I don't want to write f of x all the time, because math people are inherently lazy. So we're going to just rewrite this as y, if that's okay. How does y equal 3x minus 5? So that's sort of the first step. It's just a matter of convenience, okay? Then I want you to do the following procedure. Please understand this is by no means recognized by any mathematical institution. It's called the switcheroo. Okay. So if you're in like university mathematics and you're sitting there and you're working with somebody else and you say, oh yeah, you find inverse by doing the switcheroo, they may look at you slightly funny, and that's okay. Okay. When I'm talking about the switcheroo, what it's going to look like is this. Honestly, everywhere you see an X, you're going to turn it into a Y, and anywhere you see a Y, you turn it into an X. Okay, so we're going to do the switcheroo. So when I do the switcheroo, can you see it turns into X equals 3Y minus 5? Now, this is just a process that's going to allow us to find the inverse of this function. All right, what do you think we're going to do next then? Monty. No. No, we don't need it. It's funny you that say that, because 9 times out of 10, you're right. If you put 0 somewhere, something good's going to happen. Usually that's true. No, Tom. Interesting. Thank you. What do we call that?
Isolate the variable.
We isolate the variable, get y by itself. Can we, you ready? Can we resolve this linear function, but solve for y? So you did the switcheroo, and now we're kind of undoing the work that was done, which is kind of where we're at, aren't we? And when we redo this, don't we end up saying, well, I guess initially this becomes x plus 5 is equal to y, right? Sorry, 3y. So x plus 5 is equal to 3y. And then when you're solving, you're going to divide both sides by 3. And at the end of the day, you're going to say to me, oh, y equals x plus 5 over 3. And guess what? That's the inverse. Oh, Toby likes this. This is good. This is pretty tidy. It happens pretty quick, right? We like it when things happen really quick. It's not always that friendly. We do have issues that are going to occur in the near future. Okay. That's true. Because if there wasn't, I wouldn't have a job, right? Okay, here we go. So now that we've done that, I think it's important for us to recognize too, this is just working with a very linear function. Can you see that things could get a little bit more dramatic and concerning when we change the nature of the function that we're trying to find the inverse for? Okay. All right, here we go. Here's the first one. So this, by the way, is the technique for finding inverse algebraically. Okay. I do want to show you something here. Oh, I'm not ready for it. Let's do something else first. Here we go. So I'm going to give you a new function. I'm going to make it a little bit more provocative because I'm going to put the word consider in front of it. So consider the following. It's kind of a shout out to Bill Nye the Science Guy. Okay. So consider f of x is equal to the square root of x. Okay. Okay. Consider f of x is equal to the square root of x. And then right away, like, I want to train you, like in your mind, I want you to think about what this function looks like. And it looks different than the previous example because they were both linear functions. Like, we like linear functions a lot. This function has some issues, though, doesn't it? If I recall from all the times I've asked you to sketch this, and I'm going to do it really, really quick, this function starts at 0, 0, and then it's 1, 1, and then it's 4, 2, and I'm not going to bother with the rest, but can we see it's a parabola that's fallen over and lost an arm? And then right away, when we think about this function, it's got a domain and range, doesn't it, right? It has a restricted domain, right? In the sense it can't get to be anything. And if I'm going to describe the domain here, just because I'm going relatively quickly, is it safe to say that x just has to be greater than or equal to 0? I know this is my shorthand. It's not my formal solution. That's just the domain for this question. And then interestingly enough, and maybe it's not the greatest example, what's the range for this function? What are the possible outputs? Sure. Or welcome to the dark side, just y greater than or equal to 0. Either is fine. I will accept both. Okay. Well, if I said to you here, my trouble with this is if I ask you to consider uh, y equals, and we're trying to find the inverse, right? We're trying to find the inverse of this function. And it's funny because I think you already know what the inverse of this function is, but something bad happens when we find the inverse of this function. If I follow the rules that I told you, you're supposed to, well, I guess initially rewrite it as like y equals the square root of x. Then you do the switcheroo. And when you do the switcheroo, you get x is equal to the square root of y. And then what's the math process that undoes the square root, the square, right? So interestingly enough, like when you subtract something, the inverse of to subtract is to add, and the inverse of to multiply is to divide, and the inverse of to square root is to square, and vice versa. Here, if you want to solve this, you have to do the inverse. And when you do the inverse here, you end up with x squared is equal to y. Why is that a problem? That's a parabola. Did we start with the parabola? No. So if I sketch this, so just so that we're clear, so there's no misunderstanding, so we can see it, I'm asking you to consider y is equal to x squared. And if I ask you to sketch y is equal to x squared, it looks like this. And then how can you take one function that has only one arm, and then when you draw the inverse of this function, doesn't this inverse have two arms? How can you start with one function and have more? Do you know what I mean? But then there's a condition here. When we do the switcheroo, we're not just switching the x's and the y's. When we do the switcheroo, your range of the first function becomes the domain of the inverse. So I know the trouble is they're both the same, but your domain has to be x greater than or equal to 0 because that was the range of the first function. So be careful of this because this will be a concern later on. And then here, when I'm thinking about the range of the inverse, the range will be based on the domain of the first. And then now all of a sudden, the problem sort of takes care of itself. Because if we travel up to my really, really shoddy sketch, when we're talking about the blue function there, isn't the domain and range of our blue function supposed to look like that? Does it honor that domain and range right now? Yeah, we're in quadrant 2, and based on our domain and range, we're supposed to be in quadrant 1. Can you see that our blue function is supposed to be x greater than or equal to 0, right? And the range of our inverse function is supposed to be y greater than or equal to 0. So that means everything to the left is not included because you can't include something that's outside of the domain. So it kind of makes sense that we lose this arm because we never had this arm to begin with. Now, do they look like inverses of each other?
Yeah.
Yes. Even though we haven't really talked what inverses are supposed to look like graphically, it just makes sense. One has one arm. It makes sense that the inverse should also have. Oh, that's really interesting. Can I write that down? So Toby says it looks like it reflects over a 45-degree angle. He's more right than I think he knows. I'm not sure what he knows. So he's definitely more right than it's interesting. What do you mean by reflects over 45 degrees? Huh. Okay. I think I'm going to give you your booklet now. Again, I'm trying to be on that line of, I don't want to show you how to do everything because then you miss the joys of math, right? But I can get you started on this first one, and we can do this first one together. I'm just going to hand it out to you right now, okay? Here we go. There's lots of different sort of questions that are in here, but I wanted to actually address what Toby suggested, okay? So, can we just grab the key points that are here? So let's do this together before we get started. So can we see we've got a point right here, and I'm actually going to write them over here. So in fact, let's just label them so there's no misunderstandings. Let's call this guy here A. I guess let's make them blue because the rest of it's blue as well. So let's make this guy A. I'm sorry, I'm boring. This is Alice, and this will be Bob, and then we've got Charlie, and then we got David, and then we've got Edward. Are we okay with that? If you want to change the letters and make them your own letters, you can. This belongs to you, not to me, okay? And I guess if it's okay, can we describe each one of these coordinates, please? So the coordinates are -6 and 0. Letter B is going to be -4, +4. And then letter C is going to be 0 and 4. And then letter D is going to be, oh, I like letter D a lot, is 2, 2. That's going to honor what Toby was talking about. And then letter E is 6 and 2. Okay. All right. Do you guys want to draw the inverse? Then all you have to do is the switcheroo. What's the switcheroo?
Switch. Zero negative.
Yeah, let's just do it. Let's not mess around. What color do we want the inverse to be? Okay, fine. So if it's okay with you, so I'm just gonna call the new A, but we'll call it A prime, sorry. And the inverse of A prime is 0 minus 6, right? It's just the switcheroo. So, and then B prime is going to be, I guess, +4 minus 4. C prime is 4, 0. D prime is, hello, 2, 2. That's interesting. Can we put that word there? What word do you think I'm going to put next to D? Invariant. And then we'll put E prime, which in this case here is going to be 6, 2, 2, 6, 2, 6. And let's use this. Oh, they want you to do the whole thing down below? Who created this? Oh, wait, I did. All right, here we go. So I guess, let's do it properly. So we're going to do -6, 0 is the original. So we're going to put the blue one back in play. So -6, 0, -4, 4. Let's plot all the blue dots. And if you guys are interested, I just steal screenshots of Desmos for my graphs. I think it looks pretty good. The snipping tool is the world's greatest device on computers these days. Oh, I got lots of thoughts. Has anybody started drawing the red function yet? Stop. It's not wrong. Just stop. Okay, you ready? Here's my first question for you. Is f of x the blue function? Is f of x a function? How do you know? It's true though, right? Like, how do we know this is like grade 10 MyApp? How do you know when something's a function? Yeah, but go the other way. You went like this. Yeah. It's so that's kind of like the graphical test, right? We got a graph. So we call it's a function graphically. I'll write it in green. If it passes the vertical line test. Okay. And yeah, that's exactly what it is, function versus relation. Okay. And primarily in this course, we only work with functions because relations make math people nervous, so we try and stay away from them, okay? True story. All right. And if we take a look at this, and I'm lucky, I've got my handy dandy ruler in OneNote. I can turn this to 90 degrees to create a vertical line. And when I go along with my ruler, do I ever run into the blue function more than once? So ladies and gentlemen, it's a function. Okay. All right. Let's draw the inverse, the red now. If it only passes through the blue function once, we're good. It's safe. It's a function. Yes, yes, absolutely. That's a great way of thinking about it. And I think when we start plotting the red dots here, so we're going to dot at 0 minus 6. So 0 minus 6. And then I guess 4 minus 4. And then 4, 0. That's a problem. And then I love 2, 2. And then 2, 6. That's kind of cool. Did you not get one of those booklets, Joel?
I did.
Okay, good. So, is the red guy a function? No. Is it okay if we just call him g of x? But I can't call him g of x because that assumes you're working with a function. So I guess, can we do it this way? Can we say the inverse? Because that's the only title it gets to have is inverse. It is the inverse. Maybe, but it's not a function. That's very clear, right? Like this is definitely not a function. Like it fails a vertical line test like crazy, right? If I bring in my vertical line and bring it back, can you see it fails the vertical line test here twice? And you could argue on this little stretch here, it actually fails a vertical line test an infinite number of times, right? So this thing is definitely not a function. Can we state the domain and range of each? I think we can. I think that's a good practice for us. So if we talk about the blue function, what is the domain of the blue function? Perfect. So I'm just going to say it's -6 less than or equal to x less than or equal to +6. I know I should put x as an element of R and all that, but for now, is that okay? What is the range of the original blue function? Welcome to the dark side. Nice. Okay, so it's 0 less than or equal to y less than or equal to 4. That's a pretty good description of f of x. Do we need to see, this will be fun, do we even need to see the graph of g of x to state its domain and range? No. So if I'm right, isn't the domain supposed to be 0 less than or equal to x less than or equal to 4? Because it's the range of the previous function. And then isn't the range of this, see, I'm a liar. I can't call it g of x. I keep wanting to call it g of x. It doesn't get to have that status. It's just inverse. Sorry, you're just not that important in the math world. You're just inverse. We'll fix the problem later, but we're not going to get to fix it today. The truth is, though, the range is going to be -6 less than or equal to y less than or equal to 6. Are we better with that? 1 is a function. The red is not. So the blue, sorry, the blue is a function. The red, what I've written in red, is not a function, right? Right, right. And then there are any invariant points. Okay, I know we're getting close to the end, and that's okay. This is what I'm going to show you one last thing, because I want to honor what Toby said. Remember he talked about that whole reflex over the 45-degree line? He's absolutely right. What I want to state here so it's clear, right? Functions and inverse functions. Can we put it that way? I think a better way of phrasing it. Inverses, or even better, inverses are reflected, right? Inverses. So it doesn't matter which person you're starting with. The other person is their inverse, right? If you start with the red, the inverse of the red is the blue. And if you start with the blue, the inverse of the blue is the red. So it doesn't matter. They're inverses of each other. Inverses are reflected over y equals x. And what on earth is y equals x? Y equals x is the most boring line all time. Because y equals x is the line where if x is 0, y is 0. Maybe this is why my brother chased after me. When x is 1, y is 1. When x is 2, y is 2. When x is 3, y is 3. When x is, it's like the copycat function, right? Whatever x is, annoying y has to be the exact same value. So can you see this is a line y equals x? And if I connect this for you, can you see this is the line of reflection for our inverse function? No, because then you would have a line that's decreasing here. That's not the way that it works. But do we appreciate that this is the line? So I'm just gonna make it dotted so it like not that much though. Come back to me. There we go. Just gonna make it dotted so you can appreciate this is the line of reflection. Okay. And this is true. If you could see two functions that are reflected over this line, they are indeed inverses of each other. And I'm just going to declare the line so you can see it. This is the line y is equal to x. Kate, you have a question still? 100% right. Right. If the function crosses the line y equals x, then when you draw the inverse, that coordinate will not change. It's an invariant point. Excellent point. Excellent. Okay. All right. So this is what you're going to do. We got a nice, good weekend that's coming up. I think I said this to the other group as well. Some of you have already finished the homework that was given to you on Thursday, yesterday. I want you to work through as much as you can of this booklet so you can see, here's the next question, number 2. Going to be a slight problem with this. See what you can figure out. I'm leaving you some pieces, some gaps. And then, yeah. And then here are some of the questions at the end. I'm not going to lie to you. Well, it should imply I'm lying to you the rest of the time, but on Monday, you'll get a little bit of time to catch up on missed work because your summative quiz for me is going to happen on Tuesday. And the summative quiz, just so this misunderstanding, is only from 1.1 to 1.3. It will not include inverse on the quiz. Yeah, it's not very long. It should only take like 10 minutes, 15 minutes at most.
What is it?
So it's just going to be on transformations, shifts, stretches, reflections. So, and then putting them all together, combining them. So 1.1, 1.2, 1.3.
Oh, no, what is it?
Sorry?
On which day?
Tuesday. Tuesday. Okay. All right. And then I'll see if I can get this video up onto YouTube. Those are you guys that are in Teams. You can get it when you're in the city. But I think when you're away in a foreign location, sometimes they block you out. Okay.
All right. What should we search up for the platform?
So ask me the question again, Thomas.
What patterns did you search up and find it on YouTube?
Oh, I'll post the link on Edsby.
Oh.
On that note, I hope you guys are having a safe trip in Minnesota. I don't know.